Hi everyone, it's Sorkin. Today we have a problem when we are given a binary search tree and the key, and we need to remove from the binary search tree a node with that key. So for example, in this case, we are given this binary tree and the key is equals to 3, right? And we are removing 3 and we get this binary tree, updated binary tree without node 3. Okay, let's take a look at our first example. In the first example, we have this binary tree and our key is equals to 50. So what we are going to do, we are going to implement DFS algorithm and we are going to search in our tree. But when we are searching, it's a binary search tree. So since it's a binary search tree, all the values of the nodes on the left is less than all the values of the nodes on the right. So we are searching for 50. First, we are searching starting from the root. If the root value is more than, if our key is more than our root value, which is more than 40 in our case, then we are searching for our value on the right side of the binary tree, for example, in this case, right? So let's say that we are searching now on the right side of the subtree here for our value, and then the next one is we are searching the 50 is equals to 50. So what we are going to do in this case, we are going to, let's set up our rules. Our first rule is that if we found our value, so what we are doing, if our left in this case, if our left is equals to null, right, equals to null, which is equals to null in our case, then we are returning right. So basically in this case our left is equals to null, right? So we are replacing that with our right. So we are returning right here. We are returning right. And the same way we are doing with our right. If our right is equals to, so let's say that it's a vice versa. If the right is equals to null, then in that case we are returning left. Okay, let's take a look at the one more example. Our key is again equals to 50 and we are starting to search for our node to delete. So since the 50 is more than 40, our root value, so we are searching for our node on the right side of the subtree. So 50 is equals to 50. Now we need to remove 50 and replace it with one of these nodes. But with which node we are going to replace? We are going to replace with the right child, right? But which one exactly? Let's say that we are replacing with the 60. So we are 50, we are replacing with the 60. So we cannot do that because in that case 55 and the 58 will be on the right side of the 60. So which is in that case, it's no longer binary search tree, right? In the binary search tree, all the values on the left should be less than all the values on the right. So what we are going to do, we are going to, in our right subtree, we are going to find a smallest value, the node with the smallest values, right? So in this case, the node with the smallest values, so we are doing in order binary search, and we are finding a value with the node with the smallest value. In this case it's a 55, so we are finding a 55 here and we are replacing the value here with the 55. So we replace that. What we need to do now, so we need to again so now our key is equals to 55. Now we need to remove the node with the value of the 55, so our key becomes 55. Now we need to remove starting from the right node, right? So we are recursively calling our right root of we are calling our right subtree with the keys being 55, and we are removing our node. So again, we are searching and the 55 is less than 60. So we are searching on the left side of the subtree. 55 is equals to 55 and the left left is equals to null. So if the left is equals to null, so we are returning right. So it means that this value, right, becomes 58, and this node is no longer valid. So that's how we are performing. So that's how we are progressing in our algorithm. So we can put here our second rule. Our second rule is that if our left is not equals to null, if our left is not equals to null, and if our right is not equals to null, so what we are doing in this case, we are finding we are doing an in-order tree traversal, and we are finding a node with the smallest value. Node with smallest value. Smallest value, and we are removing that from our, we are replacing that with the value of our node, and then we are recursively calling again the right subtree with the key is being the one that we have just replaced. For example, in this case, we have replaced with the 55. We are calling our right subtree, and with the keys being 55 because we have to recursively remove the 55 in this case. Okay, the first thing that we do here, we are checking one edge case. If our root is equals to null, in that case, we are just returning null. The next one is that we are checking if our key is less than our root value. So since it's a binary tree, we are going to search for our value on the left side, on the left subtree. If the value is, if the key is more than our root value, so then we are going to search for our key on the right side of the subtree. For example, in the example that we have seen earlier, that's on the right side of the subtree. If it's not less than or more than, it means that it's equal. So we found our key. So what we are doing in this case, if the left is equals to null, right? So in that case, we are, if the left is equals to null, then in that case, we are returning the right. So if the right is equals to null, then we are returning the left. If our node has the right and the left and right subtree, so what we do in that case, so we are recursively calling, and we are finding the minimum value on the right side, on the right subtree. So for example, in this case, we have a separate method for it, and we are taking the minimum value, and we are recursively calling while our left is equals to null, and we are finding a minimum in order successor, and we are returning that value. And after returning that value, so now we have replaced that value. So now we are our root value for that, for the key that we have found, we are replacing that value with the minimum value that we have found, and then we are recursively calling our delete function now with the root right, so for the right subtree, and we are looking for the right subtree for the value that we have just replaced. For example, in our case, it was 50, right? So we have replaced that with the 55. Now on the right subtree, we need to find the root, we need to find that node with the value of 55, and we need to remove that, and after that we will recursively call again root delete node function, and at the end we are returning our root. So what's the time complexity in our case? It's binary search tree, so on average it's a log of n, but in the worst case it's going to be n, and for the space complexity is determined by the size of our stack, by the size of the recursion, and it's going to be again log of n on average, and in the worst case it's going to be of n. Okay, that's it for today. Hope you like my content. If you like it, please hit the like button and subscribe my channel. See you next time. Bye.